Okay, baby, so in this video, we're going to talk about how do we solve quadratics when the numbers are perfect squares. So how do we solve a quadratic when the numbers are perfect squares? So what you're going to learn is when to use the square root method and the factoring method to solve quadratics. So we're going to talk about how to solve quadratics by factoring, why do we solve quadratics, and how to find roots, x-intercept solutions, and zeros. So the only new word here is, we know we solve quadratics to find the x-intercepts, and factoring a quadratic is what we're going to talk to, and this is when the quadratic, is broken down to two binomials. And we might get something that goes like this, x plus 4 or x minus 4. And we may even get something with an x plus 4i and an x minus 4i. Okay? That is when we take a quadratic and break it into binomials. So x squared minus 16 and x squared plus 16. That's what it means. It's taking this quadratic and breaking it into a binomial. All right, we already know the square root method. We normally use that when there's just an x squared in the equation. And then we have a situation, what is a perfect square? A perfect square is any number that has a square root. Any number that has a square root that is not a decimal. There we go. Any number that has a square root that is not a decimal. For an example, perfect squares. 4 is a perfect square because the square root of 4 is 2. 16 is a perfect square because the square root of 16 is 4. 25 is a perfect square because the square root of 25 is 5. And then you can keep that going. And the other words we already know. Okay, so here's the first question. It says, which method is best to use to solve the quadratic and why? So normally we would go to the square root method here because this is an x squared here and it's the only thing in the equation. So we can go to the square root method, but there's an even faster method to deal with. So the first thing you look at, if the number here is 1 and this is a perfect square, because 1 and 9 are perfect squares, we actually can factor this. So the perfect squares are going to be, the square root of 1 is 1, so I write 1x. The square root of 9 is 3, so I write 3 here. And then I'm going to write 1x and 3 again. Now, since this is a plus, when I factor this, is not going to be a real root. So we're going to say plus 3i, because that's a positive 9. We're going to say minus 3i. And we're going to set that equal to 0. So here, we're going to use what is called, the best method to use would be factoring. Okay, so the best method here to use would be factoring. And we would say factoring. And that is because 1 and 9 are perfect squares. And here's how we're going to do this. So we're going to solve it like this. The square root of 1 is 1. So I'm going to put 1x. The square root of 9 is positive 3. And since that's a positive 9, we're going to stick an I on here. And then we're going to do the same thing again. The square root of 1 is 1. And the square root of positive 9 is, we're going to say minus. And there we go. And we set these equal to 0. Now we're going to take 1x plus 3i and set it equal to 0. And we're going to take 1x minus 3i and set it equal to 0. And now we're back to regular linear equations. Minus 3i goes on the other side. And so we get x equals minus 3i for that side. And the 1 I left off because 1 doesn't, you can divide by 1, but 1 doesn't change anything. And then I'm going to say the same thing on this side, plus 3i, plus 3i. So we get x equals plus 3i. All right. So we solved it. What are the solutions? So we would say x equals plus or minus 3i, or you can write both of the answers out, 3i and x equals negative 3i. You can write it that way too. Will the roots cross the x-axis? No. And that is because of this I, because the roots are complex solutions. That I means that parabola is not going to cross the x-axis. So now, here's the second part of the question. It says, which method is best to use to solve the quadratic? Well, 1 and 9 are perfect squares, so we're going to say factoring because 1 and 9 are perfect squares. They're perfect squares. Okay, so now we just need to solve this then. And normally we would go to the square root method because there's only an x squared in a problem, but it's quicker to factor when we have perfect squares. So here I'm going to say 1x, and because that's a minus 9, then I can just write minus 3. Well, you could just say plus 3. And then here, 1x minus 3. And we set those equal to 0. So I say, I'm going to do that in a different color so you can see me working out math. So now I do 1x plus 3 equals 0. Set this binomial equal to 0 and that binomial equal to 0. All right, minus 3, minus 3. We drop that line. Variables belong on the left. Constants belong on the right. Negative 3. And then x equals negative 3. We'll do the same thing here. Plus 3, plus 3. 1x equals 3. And then x equals 3. So here the answer is x equals plus or minus 3. Or you can say x equals negative 3 and x equals 3. And will this cross? Yes, because the roots are real numbers, are real solutions. There's no I here. Now, you're probably wondering, why does this have I and why does this one not have I? When you see a plus here, then you know that behind the perfect square, once you take the square root of 9, you're going to put the I. So when there's not a plus there, you just put the square root of the perfect square. And then you're done. All right, there's one more type. So what happens when the number in front of the x squared is not a 1? So this says, what's the best method to use to solve this quadratic? We're still going to say factoring. Even though we could use the square root method, but the quickest way is factoring, and that's because 9 and 16 are perfect squares. And we can call them perfect numbers as well. They're perfect numbers, or you can call them perfect squares. So if I solve this, then the square root of 9 is 3, so I write 3x. And then the square root of 16 is 4. But because that is a plus sign right here, I'm going to say 4i. And then 3x minus 4i. Set it equal to 0. So we get, on the next line, we're going to say 3x plus 4i equals 0. And then 3x minus 4i equals 0. I'm going to drop the line, minus 4i from both sides, because I want to solve for x, and I'm doing the additive inverse. And then negative 4i. And then here, I need to divide by 3. So x equals negative 4i divided by 3 in that case. Now here, I'm going to drop the line again. Plus 4i, and we get 3x equals 4i. Divide by 3, divide by 3. X equals 4i divided by 3. So what's the answer to this question? X equals plus or minus 4i divided by 3. Okay, will the roots cross the x-axis and why? No. And we're going to say because this is complex solutions, or complex roots, or complex numbers, however you want to say it. So this is not going to cross because of that I. All right, I'm done with that one. So let me clear this out so I can go to the second one at the bottom. Okay, it says in this question, which method is best to use to solve the quadratic? And we're going to say factoring again. And normally we would go to square root, but because these are perfect squares, both of the numbers are perfect squares, we're going to say factoring because 9 and 16 are perfect numbers. They're perfect numbers. Okay? So here, the square root of 9 is 3. And I'm going to put x, the square root of 16 is 4, so I'm going to put minus 4. And it doesn't matter if you put the plus or the minus first. It doesn't matter. X plus 4, set it equal to 0. All right, now I'm going to take each one of my binomials and set them equal to 0. Do my line method, plus 4, get that constant on the other side. And then divide by 3, x equals 4 divided by 3. And then here, minus 4, 3x, we drop our line, minus 4, divide by 3, x equals negative 4 over 3. So here, x equals plus or minus 4 over 3. And you can write it as 2 separate answers if you want to. And then you go here. Will these roots cross the x-axis and why? Yes, because they are real roots. No I in this one. Okay, so I want you guys to try this out for homework, and I'll see you in class, and we'll talk about it then. Bye.